in there. All right, let's play. So I have this file. It's if you want to look for it, you can. If you just want to just write it on a piece of paper, we've done enough integration. It's this Unit 7A basic integration review. I'm not going to go. We didn't officially do this Unit 7 thing, but it's a great reference. I wanted to bring up what we skipped because you might remember we kind of did Chapter 6 by the way that my notes are numbered, and then it jumped to Chapter 8, and you're wondering what was going on in 7. Well, 7 was the idea of area integration, talking about area and ways to approximate area so that you can understand where the formula comes from. And I just think throwing that out there first actually is a little confusing because it seems like you're learning this wonky way to get area that, man, it seems really imprecise and ridiculous, and then not understanding the concepts or the use behind it. I think understanding that integrals are antiderivatives is a great place to start, and then finding there's this tie between area and antideriving, which is pretty fascinating. I'm going to make this as big as possible, and let's play on. And if it doesn't, you'll have to use your microphone now because I kind of, or I guess the chat will pop up here. Don't mind me, I'm just getting closer in the corner. These are Riemann sums is the word that goes with it. So when this is not going to be showing up for you. You won't have to accomplish anything with this. I just want to show you that if I say Riemann sums and the word ever comes up again in your future, it means to use rectangles or some kind of other geometric shape, could be trapezoids, to get these areas. So if you go down just a little bit on this page, there is, so it says trapezoidal, it says Riemann sums with rectangles and things like that. Let me show you in multiple choice example, whatever this is, example 1. Those are rectangles over there trying to approximate what we actually have already learned how to do is get the area between -3 and 2. And maybe I'll put that in that pink color. It's a little easier to see. But that region right there, we know how to do this. And if I did it exactly with the antiderivative stuff, if I knew what that equation was, which isn't probably too hard to find, looks like a parabola that's been shifted over a little bit to the left one and up one. But the area with those rectangles, I could just count them. This would be Riemann is making rectangles. These are called right rectangles because of how they touch. They touch on the right-hand side. So the language that you're being introduced to is how I could actually approximate area just by putting little rectangles underneath there, knowing it's not a good approximation. But it's actually the beginnings of how all area is calculated and what the integral symbol stands for. The integral symbol actually stands for, I'm going to call this function just f of x because I don't want to write out the whole function as it is. But what it stands for is f of x is the determiner of how high these rectangles are. So notice like I could make a point right here, and maybe I'll do that in that slightly different color hue of purple. But each of these rectangles touches at its right edge, and I could find out the height of that rectangle just by putting the x value right underneath it into the function. So I could put 2 into the function and I'd get out 10, and if I put 1 into the function, I'd get out 5. If I didn't have this graph sitting in front of me, or if I was like it didn't hit exact whole number of points, I could just put in the x value underneath it. The function is determining the height of each of these rectangles. And if you notice, each of the rectangles is 1 wide. They're all just 1 unit wide. That's it. So the way I'd look at this is I get that area, the approximation of that area underneath there, by just adding together rectangle 1, which is 1 wide by 2 tall, plus the next one is 1 wide by 1 tall. It's that little one that's right here. Maybe I'll color them in as I go so you can see where I'm at. And then there's one that's 1 wide by 2 tall again, just a different rectangle. It's right here, same as that one. And we'll make our way across. And 1, 2, 3, 4, 5. So that's 1 wide by 5 tall. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So 1 wide by 10 tall. It is just adding those up. And we're going to get a number. 2 plus 2, what do you have here? 2 plus 1 is 3, plus 2 is 5, plus 5 is 10 more, and 10 is 20. All right, we got 20. You can count the rectangles, too. So if you count it up, there would be 20 rectangles or squares that we've added to make up this area. Obviously, that's not right. It's not the exact area underneath there, but that Riemann sum could be improved pretty quickly if we just make the rectangles smaller. So what makes the approximation better as you go, as you start using more rectangles. So if I use twice as many rectangles, and I'm putting them in here in green, I'm making them right rectangles again. And when I say right, that just means I want the right side to touch. Kind of helps you draw them. If I didn't tell you, that would be difficult to know where to draw the rectangles. Do them like this. And I'm just making them touch on the right edge. If I wanted to know the height, I could just find the x value underneath, plug it in. So you're adding these up over and over again. And the smaller the more narrow I make those rectangles, the less disastrous and off this area estimate is. Like right now, I'm off. But the narrower I make those rectangles, it's less off. Let me show you. If you look inside here, I'm going to highlight in kind of yellow. Here's the excess I just eliminated. Well, that yellow didn't work out, did it? Let's just use regular yellow. The excess that I just eliminated by making the triangles or rectangles more narrow, I actually got rid of a lot of waste in the previous approximation. Look, this is all extra that I'm not over accumulating as part of my area, so I got rid of that by making them more narrow. The area formula, the integral thing that we do or did the other day, actually has the height. The integral formula is the height times the width. The width of each of these rectangles, dx could stand for like delta x, the change in x, how wide it is horizontally. X is in it's a horizontal measure. So the delta x in these like rectangles that I just did there was 1, and then I made them 1/2 just by making them smaller. But dx right here stands for the width of rectangles that we're adding together, and the height of rectangle is determined by the function f of x. If you put an x in, you can get the height. So we talked about each of these rectangles has a height. I could just find the x underneath it to get the height. So you think of the function's value, the y value is the height of each rectangle, and the dx stands for the width of each rectangle. And did you know that this right here actually is an S for summation? It means to sum together height and widths. This means add a bunch of rectangles together. That integral symbol means add rectangles. And these rectangles are infinitely thin. If we make them infinitely thin, we can add them all up. There's a way to do it, kind of like when we did the limit definition of derivative, where you could make the tangent slope infinitely close, or the secant slopes infinitely close. You had this idea of getting really shrinking down the secant lines until it was right next to the point of tangency, and we developed the derivative formula. Well, you can do that with integrals too. You can make the rectangles smaller and smaller, and then pops out of there this formula that says, here's how you can get the exact area with infinitely small rectangles. But the formula just means add rectangles together, and they just happen to be infinitely small and thin. Kind of a cool idea that's why you would learn about Riemann sums. Should you go on, actually, and I talked with some of the folks who are continuing on, and then the Calc 2 folks who are teaching it. Drake's rearranging the calculus sequence a little bit, and Riemann sums would be something you'd bring up in a Calc 2 class as necessary. You just pick up with some integration techniques and keep going. So we're kind of just going into integration, maybe overlapping a little bit with the Calc 2 stuff, so they can get you through there. The rest of you, and now you're done. You're just getting the concept of I derive to get the slope of the tangent line and rate of change, and I integrate to get area, which seems to give me a sense of distance or accumulated distance. And we'll look at that again too. Okay, so that was what we missed in Chapter 7, was getting area, a really poor approximation of area by using rectangles. And Riemann, as the mathematician who came up with this process using rectangles and trapezoids is how it goes. If I delete all this and answer the multiple choice question, maybe just to kind of clean our palette after doing all that, I can do multiple erasures here. There we go. It says the graph shows which of the following. And if you want to know, these are Riemann rectangles, and they're right touching. And it says it would be a right Riemann, and there's 1, 2, 3, 4, 5 rectangles. We consider those 5 rectangles, even though I was counting squares. A Riemann rectangle is one rectangle, one width wide, and how tall is it? And so I think there are 5, 1, 2, 3, 4, 5, and they're right-hand Riemann with 5 subintervals. That's what's being described over there, and it would kind of give you a sense of what the area is from the x-axis up to that graph. That's all. There's other options you can do, left hand and midpoint rectangles, just telling you where to touch the rectangle. You can use a trapezoid. Cool things out there. All right, so let's get closer to one more use of the Riemann thing. It is, so when it says this, remember this means to get, if I had f of x, whatever it is, it does mean, and I'm going to draw this really fast and then delete it. It means if I'm going from 0 to 10, I should probably make 0, 0. Silly. If I'm going from 0 to 10, I'm getting this. That's what this calculates. That symbol means get this area that I've just shaded between the curve f of x and the x-axis. It could be underneath a little bit. It could account for going underneath, so you never know. So it could have a little bit above, but it's always between the x-axis and the graph. So this could also be an image of what that integral means. It means find the shaded regions, areas. The ones below the x-axis have a negative, value, negative area. You just take if its area is 10, then you make it negative 10 because it's underneath. That's the process. Now I don't want to keep those on the page because I actually have some points over to the right. And I was just giving you a check-in. This is actually giving me a plotted points. It says at x equals 0, y equals 3. I can plot that, no problem. And I'll make these really, really, really approximate. Go over 2 and you go up to 4. Just up one more. 2, 3, 4, you go up to 6. So 5, 6, I got it. 5, 7, and 7, 10. Okay, so these are the points that are on there. And it says use 4 subintervals to approximate the integral based on these. So if this is 10, which is my last one, and that, by the way, it's at a height of 7 when you get out there. That's the point 10, 7 that I've hit up there into the box, which is probably a bad idea. If I'm going to do 4 subintervals, and it says left hand rectangles, it's just telling me draw 4 evenly spaced rectangles in this space, please. And what you're going to do is basically put a rectangle between these and these and these and these in the picture. But I'm going to do it on top of the actual picture itself and make sure it touches on the left-hand side. Let me show you what that looks like in the actual graph. Okay, here it goes. This would be like the first point over the second one. Now the graph is not specifically drawn for me, so I'm going to kind of draw a wiggly line that kind of crosses these. We don't know how curvy it is. It could have big dips, ups and down valleys and things like that, and it wouldn't matter. Because all it's telling me is to do rectangles that touch on the left-hand side, 4 of them, and the left edge has to touch the graph. And the only points we specifically know are on the graph are these 1, 2, 3, 4, 5 points. So making the left edge touch there. So this is more of a linguistic thing. For those who are going on, I wanted you to have a sense of what this Riemann sum was about and what it means for left hand Riemann sums or 4 subintervals. It's trying to get that area without actually knowing the function, maybe just knowing some discrete points. Could you find the area of this rectangle and this rectangle, this rectangle, and this rectangle, and add them up to get an idea of what the area is underneath this curve exactly? Yeah, we could. Would it be right? No. It's under approximating. It's totally missing a bunch on the top. Like there's a little chunk missing of area that should be accounted for that's not by this rectangular method. So it's not a great method. We could improve it by putting more rectangles in there on more intervals. That would make it better. This one we can actually calculate. So you would say that the area of this one is, it's about the area of the first rectangle. What is, I'm going to write it in a fancy color that might stand out. I'll do purplish. That's not going to stand out, is it? But this one right here would be, isn't that 2 wide? And it looks like it's 3 tall, so maybe 6 would be the area of that one. And then the next one here looks like it's 2 wide and 4 tall, so I'm thinking 8. I'm just doing the width times the height. That's all that Riemann sums is about, finding the areas with these really terrible kind of seemingly antiquated methods. 1, 2, 3, 4, 5, 6, but those antiquated methods actually become very sophisticated very fast. This one I think is 12, you can correct me if I'm wrong. The last one looks like it's a height of 6 on this point right there. So I'm going to say it's 2 times 6. Is that the one I just did? Yeah, and then the one in there. No, it's 7. That's got a 7 in there, so that's 14. And this is me approximating those rectangles right there. And if I add them together, it'd be 14 and 12, 26, and 14. So about 40 is what this would stand for. It's not right. It's smaller than what it should be, but it was a reasonable way to go about it. Cool? So I'm going to put a more up there. Somebody said something on the chat thing. Thanks for mentioning it. It finally showed up too. I'll see it. It'll show up. Hang on. Show up, show up, show up. Bum, 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 bum. You guys can see all my screen right. Make sure it doesn't go on your line, yeah. I'm going to try and get it so that that doesn't disappear. I liked my old view better. Much for the top. There we go. Now I'll get the chat to fit in there. Thanks. Yeah, it probably is 4, 2. Yep, over 4, up 2. So I'll put it on there. Thanks, Elena. And that is 1, 2, 3, 4, and it landed up 2. And I put it in the wrong direction too, so it dropped down right here, right? Excellent. Yeah, so that makes that other one in there. So it drops my rectangle down below. To do others that way too, and that would be 6, 4, And if maybe I put these around the backwards. Maybe I swapped those around. Is that what I did, Elena? Or Hannah said that too? Yeah, I think I switched them around when I was putting them in there. Without going back, and I'll plot these real fast and draw the rectangles again, and I won't say a whole lot to it. The idea is knowing the linguistics that go with it too. So let me plot those points real fast. 0, 3, 4, 2, 6, 4, 7, 5, and looks like 10, 7. That'll fix it. Thanks for bringing that up. And then that one is 4, 2, and 6, 4, and 7, 5. Bam, bam. And then the last one, 10, 7. That'll help me keep track if I put them in there. And then the rectangles that we went with, the left rectangles. I don't sweat having to create these at all, but you want to touch it on the left side, so it has to touch the points that we know on the left sides. And they're all 2 wide. This one's 2 wide, I should say. This one was 2 wide. This one was 1 wide, wasn't it? And this one was 3 wide. So I'll put those on here. 2, and 2, and 1. And I'll finish these off. Okay, and then we'll go on to the next piece, because this is the kind of background information that makes these relatively fun. 2, and this one was 1 wide, and this one was 3 wide from 7 to 10. Beautiful. And so each of these rectangles, those peak rectangles, will recalculate their area real fast. That one there, 2 wide by 3 tall, 6. This one was 2 wide by 2 tall, correct, because it went to 2. That's the one she fixed up. Oh, you can't see what I'm working on. Thanks, Elena. Let's see what I got here. It's loading. It's the spinny ball. So when I pull that up here in a second, yep, I'll switch it back to the working in there. It's just about loading. I wish I could show you the, well here, I'll show you what I have here. It's showing Apple TV and everything else that it's not supposed to show at the moment. If I can get it back on here. There it is. Here's Ceiling Wheel, the spinny ball. There you go. So what I've done in here is I've drawn in some new rectangles, and they're really poor ways to see it, but I replotted all the points. And so watch out, the rectangles that I'll fix, I'll just point to them as I go. The first one was 6, but the second one is not 8, and the widths were off. And so I just fixed them as I went along. So this one was 2 wide, and I'll just underline what I had, 2 wide. I was just looking up at the intervals, each one, how far apart they are, and I just counted up the areas that went with them. And so 2 wide, and it looks like this one was at the point, I had the points labeled for you. This is 4, 2. So it's 2 wide and 2 tall. I'll circle what I'm at. This is 2 wide and 2 tall. 2 times 2 is 4. And then the one next to it is 1 wide, and it punched in at the point 6, 4. It's 4 tall. 1 by 4 is 4. And this next one is 3 wide. And the point that it hits up top here is the point 7, 5. So it's 5 tall. 3 wide and 5 tall. So that's 15. So now they got the right points on there, and I got off on the right track, or the wrong track when I was plotting those and just chatting away. The concept is the same. You're adding up the rectangles to do a poor approximation of the area. And instead of 40, as I've written up there, I'll put a big kind of outstanding X through that one on the right-hand side. Then what you'd find out is 6 plus 4, 10 plus 4, 14 plus 15. We're closer to 29-ish. Okay. Don't hang up on those. So let me back off for a second to show you. This is that chapter 7 that it just talked about how you get areas as the sum of rectangles. Other geometric things that we do with volume and area, when you get to Calc 2 and you do more integration, you're always finding a geometric shape that you repeatedly add up to fill up a space. So in this case, an area, we're using rectangles, adding them up to fill up the space. And so the integrals formula is finding the function value at a given x to get the height. And the width of each of the rectangles is some fixed amount. So you have to find out width times height gives you area. And the symbol, the integral symbol, tells you you're going to add them up. So it comes from a summation of things. And so move that down to the bottom. That's the concept there. And what we did in this one is if I have some fixed points and somebody says, hey, go get the left Riemann sum to approximate the area, the integral thing that we recently learned about, then you just use rectangles to do your best to get the area, because all we have are these little plotted points. So you just put some rectangles underneath there, trying to approximate what that area is. So leaving that behind to go to what we've been doing, we're doing indefinite integrals, which is anti-deriving. Undoing derivatives is you take a derivative and you want to go back and see where you came from, you anti-derive. So you just undo it. Don't forget there's a plus c at the end, because when you derive a constant, it disappears. When you anti-derive, you have to try and come up with that constant. And if you don't know it, you shout it to the world, I don't know what the constant is. You just put plus c and say it's sitting there. I could find it if you gave me some info. The definite integrals is the area stuff that we just did. So that's what we were just talking about now. So it's area between the x-axis and the curve. All right, and this formula, and I just gave you some context to what it really, this is a mini formula that says we're adding up infinitely small rectangle areas on the interval a to b to get the area between the x-axis and the graph. So it's called the fundamental theorem of calculus, and the formula that goes with it is, we say when we anti-derive, we call it big capital F. Just basically announces to everyone that you've undone this, and you put in the upper bound, and then you put in the lower bound, and you subtract them, will get you this area that those rectangles above did such a terrible job of finding. So this is exact. Up here, what we did was an approximation. We have an exact way to get it. I mean, it's perfectly exact, like not even a little off. I don't care how curvy and goofy your f of x is, this will find the exact area between the x-axis and the curve, which I think is really cool. But it does it because you use an infinite number of small rectangles, infinitely thin, and an infinite number of them added together to make this exact area happen. Okay, so when we're looking for the word, now area is a loaded word. Like if I say what's the total area, like how much paint would it take to cover it, then its absolute values, there's no negative and positive. If I say what's the like accumulation or just evaluate the integral, anything below the x-axis is negative. So we'll get to a problem later on where I'll really specify that. Just be careful. If somebody says, what's the area? I don't want to evaluate the integral. I want like the area, the space covered in the shading between the x-axis and the curve. Then that means you just use positive values. If it says evaluate the integral, then we got to actually account for things that are negative. Okay, so these are indefinite integrals. So all that means is you're going to anti-derive. There's no bounds. So anti-derive, there's no a and there's no b on the top. That's its distinct feature. And you just want to remember your undoing derivatives, and the power rule is the basic, most powerful one that we can pull out. You want to make sure you do a little algebra beforehand, like make it a number times x to a power, kind of like we did with derivatives, before you go about doing any of the antiderivative stuff. So look for that. I rewrote it before I anti-derive, and then use that skill of anti-deriving, and you can drop the integral symbol. This says, it's like a verb. We're saying go and take the antiderivative right now of this. This means go do it. When you're done taking the antiderivative, make sure you get rid of that symbol. So we're going to have 1/4. So this is going to be equal to 1/4 x to the 4th over 4. So watch out. I'm going to show you some things that are cool about this particular problem. It's to make you watch. The rule is add 1 to the power and divide by it. There was a 1/4 involved as a constant beforehand. They're separate. So I want them both to be there. I want to see if I can throw you off. But x to the 1/2, I add 1 to that, you get 3/2. Whatever your exponent becomes, you have to divide by it. And I helped a few people dealing with some issues with when you divide by a fraction, you multiply by the reciprocal. It was the most common error that happened on homework 11 and 12, which we'll get into in a little bit as well. And this is correct. This would be your antiderivative. The plus c accounts for any constant that if I want to check the answer of this, I can derive this, and I must get this if I'm done this correctly. So if we took the derivative of this, it would give us what we started with. There's some simplifying on this one we just can't avoid. Like you really need to take 1/4 times 4 and make sure you make that a 16th, and we'll multiply by the reciprocal on this one. So it'll be x to the 4th over 16 plus 2/3, x to the 3/2. plus c I. There it is, and that's a nice antiderivative. That's what it means to just integrate without any bounds in it. And you have negative exponent, which is awesome. Don't let those throw you off. Adding 1 to negative 1 makes 0, and divide by 0, and you go, oh, drats, that's no good. Do you remember this? This is the special case. This is one of those that you can't use the power rule on. X to the negative 1, or 1 over x. If you integrate that, it will be undefined if you use the power rule. You cannot use the power rule on this one. It's one for the books. This is natural log of x. So you just memorize every time I see x to the negative 1, or maybe I should write it as 3 times 1 over x. You can remember pull the constant out in front. All of these are equivalent on that top row. What you want to keep an eye out for is these are places where you stop and go, wait a second. This would be x to the 0 over 0, and dividing by 0 is illegal. This must be something different, and it is. The integral of 1 over x is ln of the absolute value of x. So it's just 3 ln x plus c. You memorize it. That's it. There's nothing to it. So the derivative of natural log of x is 1 over x. That means the antiderivative of 1 over x is natural log of x. So it's got that. Great. It's just, you knew that in the past. I'll bring it forward. Be cautious. Look out for that one. That always catches everybody. So don't let it be you. E to the x and sine of x are really slick. They're not the power rule. So when you antiderive these, not power rule problems. Even though there's like an exponent in it, it's not it's not x to a number numerical exponent. It's e to an x, and that's different. It's special. So it's not the power rule. Dun, dun, dun. The integral of e to the x is e to the x, just like the derivative of e to the x is e to the x. We're antideriving, so the antiderivative of e to the x is e to the x, and we know that that's true because deriving e to the x takes us right back to this. And then we know the derivative of cosine is negative sine, so this is a negative sign right here, so this must have been cosine beforehand, and then plus c follows at the end. So these are not power rule issues. They're memorized antiderivatives. X to the negative 1, or 1 over x, is natural log. E to the x is e to the x. And sine and cosine, you have to think, what would I derive to get this? So you work backward from what you know and love. To this little gem, the definite integral. So what changed? When I say evaluate definite integrals using the fundamental theorem of calculus, evaluating the integral, this could have negatives in it. It didn't say find the area. It says use the fundamental theorem to evaluate the integral. So we might have some negative areas involved in this, might have a negative result when we're done. That's okay. You don't change your process much. You still need the antiderivative. You still need to rewrite these before you dive into it. So my favorite things to do is pull fractions up front. I really just like a number times x to a power, if at all possible. So we'll go negative 4 to negative 2, and I'll call this negative 1/2 x squared. And then minus 3x, the minus 7/2, that's fine, or you can call it 3.5 if you like. Nothing fancy. But that just got me set for my power rule, and then when I antiderive, the fundamental theorem is in a definite integral is you're going to get the antiderivative. I put it in a bracket, and I put negative 4, negative 2, the upper and lower bound on the right-hand side of it, and I place the antiderivative inside here, which would be negative 1/2 x to the third over 3, add 1 to the power and divide by it, 3x to the second, not 3 to the second, x to the second over 2, and then minus 7/2, and any constant, the antiderivative is just that constant times x. Now the plus c can be put there for those who really, really, really like it, but because when we subtract these two in the fundamental theorem of calculus, that plus c will disappear. So I'm going to eliminate it. So it's not there. You do not need it in a definite integral. You do in indefinite integrals for sure. So be careful. When I put this symbol right here, what I've written right now just means I have taken the antiderivative and I'm going to put the upper and lower bound in. I'm not done yet. I'm on my way. And so my favorite thing to do is put the two brackets together. The upper bound goes in, the lower bound goes in, then I'll get you a number when I'm done. It'll go right there. It'll be finished. And the upper bound into this, I'll probably simplify some things. So I'm just going to use an eraser. The 1/2 over the third, this is going to become negative 1/6 right here. So that one's simplified, and I think that's the only one that was worth diving into. But when I put -2 in there, watch out. It's a negative. Both of these are negative numbers. When you take a negative to an odd power, like we have here, the cubic, it's still going to be negative. This is a separate negative. So we're going to get -2 cubed is -8, but it's going to become a +8. So I'll just write 8/6. Simplify later. The next time I'm putting -2 into x, where x squared is, you have to put the upper bound into all three pieces. First, you put the upper bound into the antiderivative, then you put the upper bound into the antiderivative for all the x's. So however many x's you have, make sure you're putting the upper bound in there for each one of those. All right, and when I do that, on the second one, -2 squared is 4, and then 3 times 4 is 12/2. So I'm going to put in here, and it squared away that negative. I'm going to leave a lot of steps unfinished just to make sure you can see where it's coming from. And then the -7/2, if I put that -2 in there, it'll become a +14/2, which will simplify, of course. Okay, so put in the upper bound in for x for each one of those. And the lower bound goes in. So now I'm dealing with the -4, doing the same kind of thing. -4 times 4 is 16, times 4 again. So if we put them all in there, make sure you guys just keep track of the most common error that I run into is folks that put it in their calculators and they like forget the negative is being part of what's cubed, and so they'll put down a +64 accidentally. So just make sure when you're taking it to the power 3, if you use your calculator, put parentheses around that -4 as you plug it in there. So it becomes a -64 with a negative in front of it, which is a +64/6, and that's just 4 cubed. And then -4 squared is squaring, makes it a positive, so it's -3 times 16. And again, this one, if you use a calculator, there's no shame in that. Just be really careful with parentheses. Just overuse and abuse them would be my recommendation, because you're going to have time to work on your next assignments where you have the comfort of your home to do that, and it's a great time to take advantage. And the last one, of course, 28/2. 4 times 7 is 28. Done. That's the effect of you. The thing to watch out for, and the reason I like this particular problem, is your antiderivative is pretty straightforward, but putting the upper bound in, it has negatives in it. You put the upper bound in for each x in the antiderivative. You put the lower bound in for each x in the antiderivative. Then you subtract their results separately, and then you just be really careful about how you put those in there. And if I'm typing in my calculator right now, for instance, I should probably show you guys what I have on there, so I could do that. But I'll pull up how I type them in there. There's a few help sessions that I walked through where calculators got the best of us, so now we're going to focus here in a minute. And it's coming. Let's wait for it. Wait for it. It came. There we go. Ugh. It was just hidden behind there. Like that. Look at this. This is high tech right here. But it's faster than me pulling up the other one. So if I type this in here, and you guys laugh at me for doing this, but if you're typing in fractions and things like that, you guys have some pretty fancy new calculators. You might want to use the alpha y equals key, and you can pull up that fraction that goes with it. Or when you get, so I'm just going to use one, for instance, like 8/6. And I type it in there, and I minus the next number, which is, I'll switch over to in a minute. What was our result just a second ago? Minus 12/2 plus 14/2. So minus 12/2. And I'm not simplifying kind of on purpose here. Oops. It's funny to look at when you're looking at it from the side. Okay. All right, we'll just put 6 in there because I have enough time to type that one in there. And then the 13 says 7.5. But I want to put one more fraction in for you. There you go. So when I type that in there, so that you have that super cool new calculators, go for it. Those are always nice. You get 11/6. If you don't use that and you get a decimal, there's the math button that has this frac and decimal business. So it can turn it into a fraction, or it can be a decimal. So if I have 11 divided by 6, and you get a repeating decimal, that's a sign that it'll be a fraction. You go math and frac, and it will become that fraction that goes with it. I mention that because when we get to the WebAssign assignment that you guys took on the other day, they were requiring fractions in a few places, and all I had to do was introduce a few of you to just taking a decimal that you had truncated that was a repeating decimal, or something that already was like, ended after so many digits, if it terminates or if it repeats like this, it will turn into a fraction, and you're more than welcome to use some tool to make it into a fraction. I think that's healthy at this stage in the game. So going back to this one, type it into the calculator, get a result, and which we will. We'll come back to all those when we're done because I have the solutions key on the next page that I'll send to you guys, and you guys have access to it already. Now, going on to 7, another definite integral. So you're contrasting, like, all right, if it says evaluate the indefinite integral, there's no endpoints, and I just do the antiderivative. Cool, got that. If it says evaluate the definite integral and it has bounds in it, it means I'm going to get some kind of number, and I need to do the antiderivative with the upper bound in first, and the antiderivative with the lower bound in second, and subtract the two. That's the fundamental theorem, and you're going to get a number. And you're going to totally use a calculator, and you're going to be safe. Okay, so the next one, don't look at these and panic. Just start thinking of what algebra tricks have we learned along the way. Make sure that you always split these up, make it x to some power, take advantage of the power rule. We're trying to get good at it. So if I integrate this, it would be x to the third over 3x minus x over 3x. Still from 1 to 3. So that's a great rewrite. And then ultimately, this is really what I wanted to get to. I want x to the third over 3x is actually x squared over 3, which is 1/3 x squared. That doesn't get you too far off. And then x's cancel in that last one here. So those will cancel, be negative. It doesn't cancel to 3. It cancels to 1/3. Watch out for that. Fractions can always get the best of us. And then when you antiderive, then you're going to add 1 to the power and take that and divide by that same number. I'm setting myself up with knowing I'm going to have to get the antiderivative and then continue on. So I always put the brackets next to say, all right, antiderive, do all that fun stuff, which I kind of like that rule. Add 1 to the power and then make sure you divide by it. Double check yourself. Always make sure those powers in the denominator match. Constant just gets an x tacked to the right of it. Now we will put the upper bound in for both of those x's, and we'll put the lower bound in for both of those x's. And so I set up my double brackets in any definite integral. I will simplify these. This will become 1/9 x cubed, and so we get 1/9, and it's 3 that I'm subbing in here, so it's 1/9 3 cubed, which is 27. And then minus 1/3 times 3, and let's go ahead and call that 1, because we can. And that's me dealing with this one. And I put the upper bound in. Don't forget to put the lower bound in, just because this is what would be a common mistake. You just put 3 in twice, and you're subtracting. My brain tells me I just did the fundamental theorem. I put something in twice, and then I subtracted them, but you didn't. You want to make sure you put the upper bound into the 2 places necessary in the antiderivative. Now we still have to put the lower bound into the 2 places separately, and then we'll subtract it later. But I bet you can recognize the simplicity of that, but it's easy to goof that up. 1/9 times x, 1 to the third is just 1/9, and 1/3 times 1 is just 1/3. And then from here you can type it in, do whatever you need to do to get that value. What I'm doing here is actually modeling that I don't need you to do fraction magic for me, but what I'm going to be grading on when I want to see a definite integral in your antiderivative, I want to see all these steps. The last piece, you getting me the end result, the answer, is how well you can type things into your calculator and get a fraction or a decimal necessary. I'm thinking of when you get to the WebAssign portion of the final. I want you to, you'll have more than one try, as you have on the homework. But if you get an error and you goof up, the first thing you just think of is, check your work, make sure you're good there, and then also be careful if it was supposed to be a fraction or a decimal that was supposed to be placed in there as well. Okay, and so those are all good things. The next possibility, all right, let's talk about, we did indefinite integral. We can do that. Great. Definite integral gives us a sense of accumulated area above or below the graph. This one is a different thing. This is, I have f prime and somebody's asking me to find f of x. That means antiderive, please. So there's nobody throwing the integral symbol in there. It's entirely up to us to know that, oh, I'm antideriving. I'm applying all this stuff I've already done multiple times today. So you're welcome to say, oh, I need to integrate this, because you're right, that's what you need to do. If that makes you feel better, that's the process we're going to go through. But you don't necessarily have to write that. You need to run through the rule that is involved in that, because this will give us some f of x plus c. Notice there's no bounds, so we're looking at this as just anti-deriving, and I don't have a bound, so there's going to be a plus c involved. But what's nice about this one is the fact that they gave us a point, we're going to find what c is. We're going to be able to find out the value of c. When you take an anti-derive f prime, you are going to get f of x. So that's the problem is, right now it's plus c until we incorporate in this known point, because remember what you get is the family of functions that look just like f of x. They're just not sure quite which one I'm supposed to pin the tail on. Like, do you mean this one, this one, this one? So they're going to give you a 0.12, which says, oh, yeah, this one right here. Plug it into that one. That's the function I need. So it's anti-derive, and that means 1/2 x to the third over 3 plus 3/4 x, oops, skipped a line, 3/4 x squared over 2. So that's the power rule plus c. So if anti-derived, it's a big mess. Things that I need to deal with are, my fractions. And then I need to find c, because they gave me a point. If you're given a point in f of x, you can find the plus c that goes with it. So this is 1/6 x cubed plus 3/8 x squared plus c. And that's my f of x at the moment. But what I'm missing is I sure would like to know that plus c, and I've got the info I need to find it, and that's the point. Remember, this is the same thing as 1, 2. We haven't done this in a little while. We learned that way back in the old days. It's the same as a coordinate point, x equals 1 and y is 2. So I'm going to go down here, and we're going to sub that into this function. So get ready and solve for c. So sub in 1, 2, solve for c. And we've anti-derived, and we can actually find that. So what I'm going to do is I have the luxury of writing in different colors. So I'm going to say, hey, I'm going to put 1 in here for each of these x's, right there. And then what I know is that when I'm done, it's going to give me 2 as an output. So I've been given an x value that I put in for the x's, bam, bam. And then I know that I'm going to get a result of 2, and I'm going to be able to solve for c when I'm done. So ready for this? That would be 1/6, because it's times 1 plus 1/8, or 3/8, sorry. So in the end, it's 1/6 from putting it in the first one, plus 3/8. 1 squared is still 1, plus c equals 2 is the equation that I have. And if I do common denominator business, this ends up being, that's 8 plus 18, so 26 over 48. Adding those two together, plus c equals 2. And I just did a cross multiplication thing. You guys can do a different common denominator, that's fine. And then you subtract to get c by itself. And 26 over 48, if you like simplifying these down, but I'm going to go kind of raw until I get my number all by itself. Therefore, c is whatever 2 minus 26 over 48 is. Okay, so I found c by putting in the x that I had, knowing that when I put that 1 in, I'm going to get 2 as my output, and then I had to solve for c to get it. So here's what I got, 1/6 plus 3/8, so I added those together. Old school, I did 8 plus 18 over 48, and then I subtracted 26/8 over to this side, that's my c. The final result is, when it says find f of x, is you are going to write, my f of x is, dun, 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 look, it's got to be proclaimed when you're done, is 1/6 x to the third. I like how messy, like seemingly messy this is, but it's not. And you can leave it as raw and unfinished as you like. It's funny how we get into some trends here. I'm working on this deck in the evenings, so when the weather's nice, I'll go outside after I talk to you guys and I'll work on a deck. And raw, like cut wood on a deck, I don't know. Gotta like that. It's just awesome. Looks so cool. So I'm trying to get some more raw looking pieces as I go out and shop these days. So let's leave the c raw in that, guys. 2 minus 26 over 48. That's my c. You want a number? Put it in the calculator. Go find it. It's up to you. You can frack it at the end if you like. But I don't want you to get lost in fraction and subtraction and other ideas. I want you to know that you put the x and y in, put x in for x, put the y on the end, set it equal to that, solve for c, And once you have c, your expression is complete. We just found the real f of x, not f of x plus c. No, we found a c as well because we were given a point. We could pinpoint it. Okay. There's motion. So let's talk about, we can antiderive to talk about motion a little bit. So this is a fun one, acceleration. Teaching Nora how to drive. We drive every day. She's 14. And if you aren't from Iowa, Iowa is, you could call it maybe innovative, you could call it backward, you could call it whatever you like, but they allow kids to drive at age 15, which was not the case when I was growing up. When I was growing up in Colorado, 16 was the earliest you could get your license. And I dreamt about it when I was from 12 on. Nora is 14 and she gets to drive when she's 15. Freshmen, 15-year-olds can drive to school. You get a school permit, only 2 school things. Well, yesterday I took her to a parking lot and she's been driving a little bit in the neighborhood. And I said, it's time to know what cars can do. I said, punch it, see what you can do. And we had this conversation about velocity and acceleration. So I said, oh, I'm going to have to tell my calc students we're living it right now. And for her, it was fun because what's not fun about accelerating in a car? It may not be as fun for some of you doing it the calculation-wise, but it's fun in a car. Okay. So when you take your job is, they gave me a point. I have acceleration, and it says find the velocity at t equals 4. You know that when we derive velocity, we get acceleration. So if you want to undo that, you antiderive acceleration to get velocity. So we work backwards. So if I antiderive the acceleration equation, then I just use the power rule, 6t squared over 2, add 1 to the power, divide by it. There's a constant, 22, so tag a t to it. The plus c is necessary in this, but we're going to find it. Because we have, in the velocity, I know when velocity is, the time is 0, I know that the velocity is 24. This is just like the last one I did. And by the way, I'll make this 3 here in a moment, so don't lose track. I just know that I will get 24 out when I put 0 in for t, and I can solve for c, because these two both become 0 by plugging it in there. So this one's really nice. I love when you get time is 0 or velocity is 0. It makes your solving a little easier. So I put 0 in for t. I set the velocity equal to 24. That's my output. And I solve for c. In this case, c is 24. So when it says, what is the velocity equation, then you want to make sure you incorporate that brand new c that we worked so hard for. And that's plus, what, 24? Done. And you might remember, if you've taken some intro physics class, they would even call this your initial velocity, and they'd give you the formula. Just think they would actually tell you that in this particular formula, the initial velocity is always the number you add to the end anyway. So at times 0, at the initial times 0, the velocity is 24. Some of you just say, oh yeah, we just tack a plus 24 to the end. But we did it with some calculus, made it look more interesting. It wasn't the end of this question. So you're finding when you do some of these online WebAssign things, you get one right, and then there's that extra question. So it's just remembering, this is great. I got the velocity equation right here. Love it. But it does say find the velocity at t equals 4, so you're being asked to employ it now. So you want to put 4 in and use your calculator very carefully. If it asks for a fraction or decimal, just look out for that kind of detail. You just make sure you sub it in nicely, minus 22. I won't even finish that out. I just want you to know that's what's being asked. Get me a number and enjoy it. There's units sometimes required. This one didn't say, so it could be feet per second, and it could be feet per second squared for acceleration, feet per second for velocity, or miles per hour, etc. All right, so those are the big review ones I wanted to peek at real fast. There's, I think there's a couple on here that are actually pretty simple on here, but I'd rather go back to the homework. So this review is out there. It's called the Chapter 8 review, and it's got the answers all worked out. So you can see cleaner, nicer versions of this already worked through and in nice color as well. So if you want to see something better, I just want to make sure you understood when I say antiderive or use the fundamental theorem, these are the big ideas we've covered. Everything's here. Indefinite integral means antiderive. Got it. Check. Definite integral means find this area between the x-axis and curve. It could be negative or positive. It means this thing. And then it says just antideriving. If you have f prime and somebody says go find f, well, that's antideriving. You could put an integral symbol in there if you want. You don't have to. Same thing, acceleration to velocity. That's a form of antideriving. Now, let me bring up homework 11. This is your chance to chime into things. Here's my homework 11. What's your homework 11 look like? I just printed it beforehand. It's got all this date and time stuff written up there. So I'm gonna get my chat in view, but it doesn't like, I did that last time too. It wouldn't show up on the big screen. So we'll see if I can, when you guys do something and I'll skip out of the screen. It's just when I cancel here, all kinds of weird things happen. There it is. Isn't that funny? I don't know why it does that. It's there now. Excellent. That's my actual assignment. So find homework 11, kind of think about your questions on homework 11, because that's what I'm going to ask next, is to see homework 11 questions pop up. And I'll see if I can get my air server to show properly. There we go. That's the one I wanted. Okay, so putting the three, Hannah's got a cool one. So would putting the 3 in the absolute value be wrong? Ooh, were you looking back at the one we just did, Hannah? Is that what you're talking about? Sorry, I didn't see that earlier. Let me know, and I can see your chat now, so if you ask, I will actually respond this time. Or maybe I won't. Maybe I'll just get snide and ignore once again. Oh, number 4 from the review. Thanks. All right, let me pull that up. Rolling. Number 4. Oh, yeah. So you're asking about what to do with this one? Yeah, so number 4. So would putting the 3 in the absolute value be wrong? Oh, yeah, inside it. Yeah, a 3 goes in front. So you think of it as, and maybe I'm not answering this right, but you just let me know. This is a constant that was part of the problem from the beginning, and you can always just pull it out front. So I did at the end. The integral of 1 over x, the antiderivative of 1 over x, is ln of x plus c. And the times 3 was separate from that. Is what I was going for. There was no number to substitute. We aren't doing a definite integral here. This is just anti-deriving, and the antiderivative of 1 over x, or x to the negative 1, is a special one that you want to remember forever. And it is the natural log of absolute value of x is part of the antiderivative formula. Maybe leaving that detail of y for another conversation at the moment. Bring me back to that anytime you want. Homework 11 is back. So yeah, it says if the x was being added to something, would the entire thing go into the absolute value? Oh, so if like the expression initial integral was like 3 parentheses x minus 1 to the negative 1, is that kind of what you meant? And I could write it on the, here, I'll write it on the sheet because I've got it up in front of me. So if I did the 3, and I did x minus 1 to the negative 1, is that kind of what you meant? Yes. Oh, yeah. You have, and if you guys don't know, Hannah's got some calc experience in the background. Yeah, this ends up being 3ln of the absolute value of x minus 1. That only works, that is absolutely 100% true, but only if this is linear. So that has to be a linear function and it's really direct, and x has a coefficient of 1. If not, we have to do something called u substitution, and that's a Calc 2 topic. Right away, you get into this thing called the substitution method of integration. It's a tool to dealing with this. So if linear and the x coefficient equals 1, then this is the antiderivative. Whatever is inside here, if it's just plain old x minus something or x plus something, the integral is just 3 ln of whatever's inside those parentheses. Yeah, that's a cool one to look at. If that came up somewhere else, I'd love to know too. So how about 11? Do you guys have anything on homework 11? So chat's perfect. Yell something out if you want to. But I'm interested to know, was there anything on 11 I can work out? I actually have it pulled up. Like, I will just do the problem. So if you want to see one, this is your chance. And if there's multiple ones that come up, that's even better, because then I can see repeats. But I have 12 as well. So if we just really, really want to get to homework 12, say that. Say homework 11, number 7. Homework 12, number 4. Go for that. I'll give you a second to think about it. And I'll bring up the background music. We'll make it feel like we're, in the waiting office, getting onto something. I've had the goofiest things happen in some of these online. I really like this one. So those of you guys are some homework 11 number 4. Absolutely. So my homework 11 number 4 might be different, Elena. So let's go there for sure. I'm playing this song right here. It's called Therapy, which I really like. If you guys like Rent, this is the original musical by the composer who did Rent. And Raul Esparza is an awesome performer, so I'm kind of a big fan. But that's the one I wanted to play earlier today, and I got in the mood instead, which I think is a pretty good trade. Okay, shall we? Next thing is number 4 on homework 11. Homework 11, number 2. Done. And I'll just keep an eye on this for you guys. And 4 is asked for first. And we'll go to 11. And you can just pop them in there as you need. Grab something to drink if you're waiting in the meantime. All right, let's go 4. On my 4, it says you're putting in these values, and it's a big pain. It's like asking you to do a whole bunch of these inside here. So you go 6 to 0. So this one means the integral from 6 to 0. So if even the context, I think, is really funny to follow. It's just a shorthand way of saying, I want you to do a whole bunch of these. Have fun. And this would be 6 to 3. Go find that one. Good job. And then the next one would be 6 to 6, and so on. So, and there's some ones that you are pretty quick and easy that you can eliminate right out of the gate, which I'm going to show you as well. So if you do number 4, there are ones that are similar to this. It doesn't mean, frankly, if I give you a question on this, I would just give you all of these integrals separately, which I had. So it's like the ones we did in some notes. They were all just written out separately, and then the picture is down below, but this is just a way of saving some space and time to put it all in there. So interestingly enough, there's the whole backwards thing going, so I'm going to highlight this one's really cool because it's like 0 to 6, but it's backwards. So when you go to 0 to 6, you're going to look at, this is the region right here. It's positive, but when you put the bounds backward, you end up with a negative result. So, and it's a funny thing, and it says which of the following values is largest. I just got done with this in another assignment that Nora was working on. This is just going to end up being a negative number of some kind, and you just have to compare it with all the others based on its size. Value is on the number line. So when it says smallest to largest, the numbers on the left of the number line will be smaller than the ones on the right side of the number line. And that I don't think is clear, because I'm just thinking maybe like magnitude 10 and negative 12. I would think negative 12 is just a larger value, but no, negative 12 is smaller because it's to the left on the number line, and that's not intuitive at all. So it's putting it in order. I know that this one, the one you want to jump to, just for really important things to know, like f of 6 would be 0, because the integral's from 6 to 6. There's no width, so that's definitely 0, and I would really want you to be able to note that in the future and say, oh, that one's 0, done with that one. And then let's see, which one is the largest? Well, the first one was really kind of a big negative number, so I'm going to look for the one that makes the largest positive that goes with it. And on this one, just to finish off the problem, I think the largest one, if I do 12 from 6 to 12, that's pretty negative. Goes with the other one. And then 6 to 9. And then the one that's from 6 to 3. Ooh, I like 6 to 3, but it's backwards, so it would be negative. Is there one that's positive in there? That would be the one to find. If we could find one of these that is actually positive, then it would be really straightforward and we could find the result of this one. But I think the largest of these might be the one that's the least negative out of all of those. It might actually be this little dude on 3 to 6. And if I open up my assignment, I can go in and check these too. But the largest can be the one that is least negative, because it appears that all our results are negative. And mine, since I've got it involved in here, I want to put it in there and check it. If you'd like to see yours, Elena, worked out, I can do that. I can pull up yours and send it to you and actually work through yours. And if that's of interest to you, let me know. But that's the concept, and I don't, without getting lost in those details, I'll help you through the problem, but you just want to know how to interpret those. Cool. And then this one, so the least negative of those two, that 3 to 6 one, if you have a chance to check it out, this one appears to be least negative of the bunch, because everything else seems to be negative inside here. Check it out and come back to me. I'm going to go up to 2 real fast, because 2 has a more direct approach to the same kind of thing, which I think is a really nice balance. So I'm glad you guys asked about these. Here, if I say, this is more like how I'd ask anyway. Hey, evaluate 0 to 4 of g of x. And here's g of x. Then you just make sure that you know where, you watch your scales, by the way. These are going by 2s. That would be an easy one to goof up. But 0 to 4 is this chunk. And you just have to know, oh, it means I need to evaluate that. 0 to 4, it's a triangle. It's 2 wide and 8 tall, or it's 4 wide and 8 tall. Watch the scale. 4 wide and 8 tall. And it is a triangle. Oh yeah, don't forget to multiply by half when you're doing area of a triangle. That's an easy one to goof up. Scale is a doozy. I'll try not to mess you up when I'm giving you my own problems, but 32 times a half, and 16. And then 4 to 12, I'll do that one in green. But I like this one better as far as here's 4 and here's 12. We're talking about this region. So it's the half circle. And know your basic formulas. Obviously, you don't have to worry about it because you can look anything up, but it's a half of a circle. So it's half of pi r squared. And the radius is, when you look at these, remember, is halfway across, not the whole way across. You need to know how far that is, and that's 2 plus 2, that's 4. So 4 is my radius of that half circle. I've indicated the half here, 1/2 pi r squared. The answers are exact that you want to put in there. So that'd be 16 times a half, that'd be 8 pi. I believe it asks alternately. Sometimes it wants the exact, which would be 8 pi. Sometimes it wanted the decimal. Yeah. And so that's 11 number 1. And what it's asking for, 0 to 14 would be the integral, would be the sum of those. And I didn't get to this last chunk. So let me finish this one off, and then Hannah, that's a great question. Let me get yours. That would be the 8, and that is a negative 8 pi when we're dealing with regions that are below, and that's just you noticing that it's negative because it's below. The 16 is positive because I notice that it's above. And then the last one is a triangle that's 2 wide by 2 tall, but half of 2 times 2. So it ends up being half of 4, which is an area of 2. And then what we'll do is you just get to sum these together. Not 2, sorry, that's the last one. But I'm adding it to my negative 8 pi. And I'm adding it to my 16. So you just put those all together. The ones that I've seen, you can potentially get away with exact by. Some of them are asking for decimals, so let me look at mine. Yeah, I have to engage it, like I have to go to the problem and click on it to see. And so we'll check that out. Ta-da! It was, all right, Hannah, yours is f of 6 equals 0, I mean. Which one were you looking at, Hannah? What problem was that? Oh, the answer is the one that is 0 because it is the largest non-negative number on the number. Yeah, so this is, I forgot, we had 0 as one of our answers, wasn't it? Thanks, because these were all negative. So I was saying the largest negative. Thanks for pointing that out, because this one ended up from 6 to 0 was negative, flipped it up. This one was negative that we just talked about. So I'm going to point out what these are. These are negative, and we talked about f of 9 was all negative. This was negative. It can be the least negative, but you're right, Hannah, because we have 0 as one of ours, that's bigger than all those, and I did not plot that on there. Thank you. 0 is bigger than all those silly negative ones that we had on ours. Good call. I forgot about our 0. And that'll help Elena, so she can put that in there. Good. The next one was 11-1, homework 12, number 1. You got it. Flipping over to homework 12. It's number 1. That's weird looking. Good. Same kind of thing, but I think this one's easier to read. So you're hitting the same theme as the one that Elena was asking about. If I put g of x is the integral, the area that's being calculated, the calculation of areas above and below for f of x. So g of 0 can be interpreted as, and I'll put it over here, you integrating from 0, and you put 0 in for x up top here. So you're just subbing in things. So whatever goes into x becomes your upper bound. So if you put 0 in there, that means 0 is your upper bound, f of x. And if your bounds, the left and right bound are the same, then it's always 0. So this one's a nice one because there's no width to that interval, so the area doesn't have any width as 0. And then the next one, though, gets more interesting. So I'm just going to kind of one by one plop these in here. So it really is a variable you get to put in. Now the next one is putting in 1. So that means you're going to put 1 up here. And then 0 to 1, then you're doing this little chunk. And that's a half of 1 times 1, which is a half. So you can slide a half in there. So this is like a nicer geometric one than the one other I had. I'm glad you asked. 2. You can take the next one and put in 2 up top here, because that means put 2 in as the upper bound. That out of there. And that result, if you go from 0 to 2, it involves a negative chunk. So you got to watch out for that. This would be, let me put the green in the right place. This would be a negative 1/2. So that's 1 times 1 divided by 2. And then the positive half on top. If you get the integral from 0 to 2, that means you add together those two regions, one being positive 1/2, the other one being negative 1/2, and you're going to get 0 as the net between those two. So that's a cool one to look at. That's what the f of 0 to 2 stands for. Let's keep going, because this is, I think, a really healthy one for all of us to look at. If I go to the next one, should I put 3 in there? So as we inch along, put 3 in. Then I'm putting in a little bit more area in here. So it's adding in that extra negative 1/2, negative because it's below, half because it's 1/2 base times height. Now that means the 2, we think of the first 2 as having a net accumulation of 0. And there's the same area above and below. The sum, when you're integrating those, is 0. So we just at 0 from those, we just tacked on another negative 1/2. So I could just simply go, oh, then that means this is just negative 1/2. Because I already knew it was a net 0 from doing the area from 0 to 2. Now I'm going 0 to 3, tacking on an additional negative 1/2 of accumulation. And then you get to 4 and so on. So it starts to, you can do it in pieces. It's actually a little easier to interpret. So if I go to the next one, which is 4, then I'm putting together the 0 of the first chunk, the negative 1/2 I just got, and now I'm putting on with it another positive 1/2, which will cancel with the negative 1/2 I currently have. So this is a net 0. So 2 net zeros together make 0 altogether. It's a pretty cool problem. That one is way better than some of the rest of these. It does say estimate GS7, use the midpoint the most to get the most precise estimate. If that one really hangs you up, just let me know. Go ahead and skip it on there, and I'll help you out individually as you go. You could probably guess as you go. I didn't want to do that. It means to do the midpoint method of rectangles. It means to find the halfway point and put a rectangle in there. So what you'd want to add, if this is your particular problem, is you need to get the area of this triangle, or this rectangle that touches at the midpoint, because they're suggesting the midpoint rectangle would be the most precise way to estimate, I should say. My emphasis in the wrong syllables all over the place today. So the area of this midpoint rectangle would be added to what you already have for the other regions that are in here. And where I'm at right now is I'm all the way to 4, and my net is 0. And so if I could find the area of this chunk right there, and then just add to it this midpoint rectangle, then I'd be finished. So let me pause for a second. I'm going to look at others that if I missed anybody. Homework 12, number 1. And some of these are private, so you guys hopefully can see it on the shared screen. Homework 11, number 1. 11. That's it. Good. So if there's others, if not, I'll finish this one. And if you think of something else too, that's 11 and 12. And individually, I'd love to help more. I've actually done quite a few of these with you guys. You've been really good about asking, because they're tricky and it can get kind of long. So keep chipping away. I know some of them are a little bit repetitive and long. Good. This is a goal that I met. Some questions that you had, went through that review, because we have this quiz on Tuesday on integration, and it is not the worst problems that could come at you. I am going to decide sometime between now and tomorrow if that's going to be what type of quiz that's going to look like, if you're going to do it on paper. I still have to get back the quiz, finish up those quizzes and email them back to you, the ones you guys did on the derivative applications. They're There's a lot of good ones in there, so you'll be excited to get them back. But you doing it on paper versus online with WebAssign and some definite tries, given that we have your final that I'm going to send out to you, the take-home portion of it. I'll get that out before the weekend, so you can be working on that right up to finals. You'll have more than a week to turn that in. And then the WebAssign version of the final, which I'll open up, it could be even next week at some point. So you have multiple days to get that finished as well. So I'm still thinking on that quiz. Do I want to do one more paper so I can see the work? It helps me get back some more minutia to you, maybe some better feedback for you to go into your take-home portion of your test. And then maybe it's better learning, I think. Will the WebAssign final have multiple tries as well? Yes. How many? Still working on that. And actually, I'm in collaboration with one of the other professors doing Calc 1. He and I are going to just chat about what he's thinking. We'll have different tests, but we'll have, we're going to give it some similar approach. So however many tries he's thinking. So, yep, I think at least 2 tries has to happen. So thanks, Riley, for asking about that. Cool. Feel free to stick around. Head off if you need to. I'm going to do the rest of this one just to finish it off and get some numbers on the page, and including the B and that stuff like that. But feel free to head off, private message, chat on here, talk, send me an email. And hope you guys have a great weekend and play a little outside. I'm going to leave here and I'm going to go put in 2 more rafters on the roof over the covered deck. I'll send you guys a picture at some point. Get your feedback. What's missing? I think what we need is a garage door for a stage for like bands to play in the neighborhood is what I'm thinking next. And only $20,000, no big deal. Just teach more classes. Okay, I'll get back to the math. Talk to y'all soon. So here is G5. We were wrapping these up. I was color coding. We got to 4 and found out that the net was 0. And then I was going to add on this lovely trapezoid here because it asked, we got to do G5. Let me do that one first. Should be getting this up to x equals 5. And so with my net being 0 right now, I only need to find the area of that trapezoid that's left. And if you're not good at trapezoids, you can make it into 2 triangles on here too. So let me delineate that. Maybe that'll make you a little bit less nervous about these. You can do a triangle and a rectangle. The triangle is a half, and the rectangle is 1 wide and 1 tall, so 1.5. We could have done any method that we like. So that little area is 1.5. Because the net up to that point was 0, then we can put in 3/2 or 1.5 if you like. Okay, that's the piece that I'm in right now. So 0 net up to G4, the area accumulated, had an equal amount above and below. And then when I said G5, we were just tacking on that pink part that I just put in there. And then when I say G6, what we're adding on is this, let's go to a fluorescent kind of green. Be this chunk right here. Another opportunity maybe to do this is a rectangle or a square of 1, this is a square of 1, and then this is a triangle of a half on top here. So 2.5 in addition to the 3/2 that I already have there. So that would be 7/2 plus 3/2, and so we'd have 10/2 or 5 total. And if you want to count them, it's kind of fun. There's 1, 2, 3, let's see, 1, 2, did I just do that right? 3, and then 4 total. I added really funky. That is 4. It really is 4. If you're laughing, let me know because it's funny. All right, 4. There it is, the area that adds on to that. So you're just doing area by adding up the spaces and interpreting it. I know is the biggest issue for those like you guys have mentioned and over emails as well. The last one, that part B, it says G7. It says use the midpoint method to get the most precise. So just think of the area up to 6, the net is 4. So if I get rid of all else on here, and I just think of where I'm at right now, and I do it in that lovely green color, the net total with all these regions added up to here is 4. Got it. And down here, what I'm going to add to it, G7 means go on and add on this extra chunk, but it's said to approximate it because we know it's a curve. It's not a triangle, it's not a rectangle or a trapezoid. So without knowing the function, now if we knew the equation that made that, we could use our cool integration techniques that we've learned, and we could take it on that way. But since that is not the case, they say use this midpoint. And so I'm going to estimate, if I go midpoint, that rectangle to me, and I think what the intention was, think a middle point rectangle touching that graph would probably be right here at 2.5, would be my guess. 1, 2.5. So it's 1 wide and 2.5 tall. So I think we just add 2.5 to it. So it's the 4 that I've got plus this 2.5-ish rectangle that I'm ballparking. I think a 6.5 is a reasonable estimate for G7, and it's not right, but it's close. So I think that's the gist of what's being asked for in there. And where does G have a max and a minimum value? You could just run down the list of these values. So just look along here and look at those and just tell me which one gives you the smallest amount, negative being the smallest and maximum being the biggest, most positive. So think number line. So max and min means minimum lowest on the number line to the left and biggest max being furthest to the right. And that would conclude that lovely problem. And it says do a sketch, a rough sketch of G. If you plot these points down below, so if you remember our first point is 0, 0, and then that's what these are. These are coordinate points. Plot all those points and make sure it matches the graph that happens here. And if you have any other insight into it as well, if you want to plot some other points and kind of do some other concepts, you can. But if you just simply plot all those points up there, you'll be able to identify which graph matches. No problem. That's really mechanical in that sense. That'll do it. Cool. Well, thanks, y'all. I see a couple of you hanging out here. You are diligent souls. Ask away if you want in the next few minutes. I'm going to run down and catch up with everybody in my house here in the next couple minutes by email or ask about another one. Send me messages if you need extensions or more time. Those are good things to ask about too. Cool. I'll stop the share and at least bring up got the check on all those questions. See you soon. You guys can see me again. One new message. Yes. Yes, the last ones. Yep. Okay, those are our last assignments. No more, other than a final on WebAssign and maybe a quiz, still be determined. So just think WebAssign could it's 1 or 2 more uses of it after homework 11 and 12, but these are the last homework. You bet. Thanks, Gia. See you, Claire.